Okay, welcome to Introduction to Statics. We'll be discussing the basic principles of statics and what you need to know for reporting your answers and that kind of information. So statics is a branch of mechanics, and mechanics is then divided into three sections: rigid body mechanics, deformable body mechanics, and fluid mechanics. So out of rigid body, we have both statics and dynamics. So statics really means that your rigid body is not in motion, or a more generic definition is that the acceleration and the deceleration is zero, so it is not moving. So in statics, we use a few idealizations to make the problem simpler. We use a particle, which has a mass. However, the size can be neglected. Then the rigid body, which is a combination of particles that remain at a fixed distance from one another, both before and after applying a load. Which basically means that no matter what force you're going to apply to this rigid body, the shape will never deform. So if you have a wheel and you apply a force at the bottom, like from the pavement, it's going to be exactly the same. The wheel's shape is going to stay the same even after you release the force or put the force on. Okay, another idealization is concentrated force. And that is loading, which is assumed to act as a point on a body. So that's the same type of thing with a wheel. The force from the pavement is going to act directly at the bottom of the wheel. It won't be distributed at all. Okay. So statics is really based on Newton's three laws of motion, one in particular, but we'll go over those really quickly. So the first law, which is commonly known as a particle in motion tends to stay in motion, and a particle at rest tends to stay at rest. of course, that's provided that the particle is not subjected to an unbalanced force. Okay, our second law is that force is equal to mass times acceleration. And now in statics, like I said, acceleration is 0. So our force is equal to 0. And this little arrow that I put above force and acceleration means that it's a vector, and we'll go over that more in the next sections. Then our third law is that the mutual forces of action and reaction between two particles are equal, opposite, and collinear. So for instance, if we had two particles, A and B, and we applied a force here, F, which is the force of A on B, there would be an exactly the same force, F, right here, which is the force of B on A. Right. All right, the next law we need to worry about is Newton's law of gravitational attraction. Which is the force is equal to G m1 m2 divided by r squared, where G is equal to your universal constant, of gravitation, and that number is 66.73 times 10 to the negative 12th meters cubed per kilogram times second squared. So as you can see, this is a really tiny number. So M1 and M2, or at least one of those masses, has to be really large for there to be any effect. So M1 and M2 being the mass of the particles, and then R being the distance between the two particles. So this also shows that since R is in the denominator, the distance between the two particles has to be relatively close for this to be a significant force, right? So we have a very small g. So if m1 and m2 are sufficiently far apart, then the r squared is going to take it down so much that there's no gravitational interaction between the two objects. So one place where we use this, the law of gravitational attraction, is in the weight of an object. So if we set the force of the weight of an object equal to W, so that's basically the force of Earth's gravitational field against some object. So that's going to be Gm, the mass of the object, times the mass of the Earth, divided by r squared. And so now we can put G, gravitational acceleration, equal to gravitational constant, the mass of the Earth, divided by r squared. And that's going to give us the equation, the weight of an object is its mass times the gravitational constant. So in SI, G is equal to 9.8 meters per second squared, and that's what you're going to be using in all your problems that have to do with SI units. And now in English units, G is equal to 32.2 feet per second squared. So that's how you determine the force of the Earth on an object, which is its weight. So let's go over a little bit of units. So we're going to be using length, time, mass, and force. There'll be more complicated units introduced later, but these are the basics of statics. So in SI units, we've got the length is meters, m. Time is seconds, s. Mass is a kilogram, and force is a newton. And a newton is just a way to express kilograms per meter per second squared. And now in English, length is going to be a foot, time is also going to be a second, mass is going to be a slug, which a slug is a pound per second squared divided by a foot, and a force is a pound. So it's interesting the difference between the English and the SI. In English, a pound is a base unit, unlike in SI, Newton is not. And it's the form of these three variables. Whereas a slug is the same thing, it's the form of these three variables because it's not a base unit. It's a derivative of these. So one way to check in a problem if you're doing it correctly is a dimensional analysis. So for instance, if you look at like F is equal to mass times acceleration. That's one of our basic equations, right? So the unit for force is a newton, mass is a kilogram, and acceleration is meters per second squared. So if you look right here, you can tell you did the problem correctly because you've defined newtons, kilograms times meter per second squared, which is exactly what we define newtons as up here. So you know that's a legitimate equation because the right side variables equals the left side variables with respect to units. So in English, if we were using the same thing, force is a pound, mass is a slug, and acceleration is feet per second squared. So now if we plug in what we know a slug is, we can tell this is a legitimate equation because the s squared, the second squared, cancels as to the feet. Pound is equal to a pound, That's a legitimate equation. So if you're ever confused in a problem, if you did it right, do a dimensional analysis. And if it comes up that maybe you're missing a pound on one side of the equation, then it's incorrect. So you need to go back to the start. All right, let's go over some numbers really quickly, like our scientific notation. So if our number is 1 billion, so that's 9 zeros, in scientific notation, that can also be expressed as 10 to the 9th, and we call that giga. And this is only for SI units that we use these things, giga and, or the abbreviation being G. But you can use scientific notation in English or SI. But for instance, if this was 1 billion newtons, you could say it's 1 giganewton. So let's just go over a few more. 6 zeros means that it's 10 to the 6th, which is mega, denoted by a capital M. 3 zeros, 10 to the 3rd, means it's kilo, denoted by a lowercase k. We can also do this with decimal points. So 3 away from 3 on the right side of the decimal mean it's 10 to the negative 3, which is milli, a lowercase m. So that's 6 to the right of the decimal place, so it's 10 to the negative 6th, micro, denoted by mu, and then 9 on the right side of the decimal place, 10 to the negative 9th, and that's nano, and that's a lowercase n. So let's go over just a few little examples. So if my number is 1, 2, 3, 4, 0, 0. In statics, it's easier to always call things out in scientific notation in groups of 3. So for instance, this can be called out in 2 different ways. We can call it out as 0.1234 times 10 to the 6th, or 1.234 times 10 to the 3rd. I think that, oh, I'm sorry, this isn't correct. It's 123.4 times 10 to the 3rd. And this is really the preferred method, right? You want to have something on the left side of the decimal point when you're talking in numbers greater than 1. So let's just do a few others. So if this is our number, we can also express it as 0.136 times 10 to the negative 3rd, or 136 times 10 to the negative 6th. Our number is 0.02836, and we can express that as 2.8346 times 10 to the negative 3rd. And we can also just 1,000, like it's the same thing as up here, that can also be expressed as 10 to the 3rd. So those are just a few examples of how you can use scientific notation. And scientific notation is really useful for when you're looking at significant figures. So let's go over significant figures really quickly. So there's a few rules for significant figures. We'll use these numbers as our examples. So a significant figure is really a non-zero number. However, there's a few special rules for zeros. So right here we've got 1, 2, 3, 4. We've got 4 sig figs, but because these 2 zeros are at the end, it's unknown whether or not they're significant figures. So in this case, there could be 4 to 6. However, if you're given a number like this, you should just assume that it's always the least significant figure, so 4. Now in this case, we've chopped the zeros off at the end by using scientific notation, which makes it really useful because now we know that we only have 4 significant figures, 1, 2, 3, 4. And a 0 on the left side of the decimal place is never a significant figure. Obviously this one's going to be the same as the one above, also 4 sig figs. Now this one, when a 0 is to the right of a decimal point, it's never a significant figure, unless it's at the end, but before the first non-zero number. So these 3 zeros are not significant figures. So that means that we've got 3 sig figs, 1, 3, and 6. In this case, it's the exact same thing. We didn't actually need to use scientific notation to prove that it was. And same here. Now this one, same thing, these 2 zeros are not significant figures. So that means we have 5 sig figs, 1, 2, 3, 4, 5. And then we also have 5 here. So in this case, like I said, the zeros to the right of a number, you're not sure if they're significant figures. So this could be 1 to 4. But in this case, just 10 to the 3 or 1 times 10 to the 3, that 1 is a significant figure. And so there is 1 significant figure in that. And so the rule of thumb that we're going to use is that your final answer should use 3 significant figures. But to maintain the integrity of your solution, you should not round to your final significant figures until the end of a problem to avoid rounding errors. So you should go through the entire problem using, basically store the number on your calculator so that it has the entire integrity, and then at the very end round down to 3 sig figs. So let's discuss how your homework problems should be submitted. So for every single problem, you should have a given. What are you given in the problem? And that should always include a sketch. Then list what you're going to find, which is list basically the objectives of the problem. And then finally, the solution, how you're going to solve it. So a solution should always be presented as variables first, and then you can plug in the numbers as you begin, as after you've simplified the problem, simplified your equations, then you can plug in the givens. So you want to list all your equations with variables. Then you're going to want to manipulate the equation. Symbolically, aka don't put in your numbers yet. Then plug in your variables, your numbers, and solve. So you will always see me do examples in this order. So if you're ever confused as to what your homework should look like, they should look like my examples that I give you in class.